Okay, folks, first day of our 8th unit. We're going to be talking about antiderivatives and integration. So remember back to Unit 4, first semester, we talked about derivatives, talked about something called the power rule, and we discovered that the derivative of a function is akin to finding the slope of the function at every single point. So our goals for today are to remember how to take derivatives using the power rule and then work backwards to figure out how we can come up with the power rule for antiderivatives, the undoing of taking derivatives. So let's remember that if I give you some function f of x equals 4x cubed plus 2, I can take the derivative by multiplying the exponent to the coefficient. So 4 times 3 gives me that 12 right there. Then I subtract 1 from that exponent to get my new exponent. So 3 minus 1 gives me that x squared. And then remember, if you have a constant term, the derivative of that is just 0. Because remember, you can think of it as an actual function. If we think of that plus 2, well, that's a horizontal line with the y value of 2. Slope of a horizontal line is 0, and so that derivative there just goes away. So if we want to do that to this function g of x, then we need to just do it to each term. So 2x to the 5th is going to become 2 times 5 is 10, x to the 5 minus 1 is 4. Minus 3 times 4 is 12, x to the 4 minus 1 is 3. Plus 2 times 2 is 4, x to the 2 minus 1 is 1, and that minus 3 has a derivative of 0, so we won't write it. And this then is our function g prime of x. So one more real quick, do it super quickly. If I have this function here and I want to find the derivative f prime of x, I'm going to take the derivative of x cubed is 3x squared. The derivative of negative x squared is negative 2x, and the derivative of x is 1. And then that minus 1 has a derivative of 0, so that is our f prime of x derivative function right there. So very briefly, some common notation here. Given a function f of x, notice the f is a capital letter. I'm going to call that big F. Given a function big F of x, let's let the derivative of big F equal little f of x. So common notation there, if you see f of x, it's saying it is the function above little f of x, like that. So by taking the derivative, we get the little f from the big F, just common notation to be aware of. So now let's think about this in the opposite direction. Write a function f of x, big F, whose derivative will be the function little f of x equals 2x. So we kind of need to think backwards. Using the power rule, how are we going to get a 2x? Well, that one should be fairly common to us. Big F here should probably be something like x squared, because if I then take the derivative of that to get little f, derivative of x squared is 2x, and so we're good. But the problem is, what if we said the big F was x squared plus 3? The derivative of x squared plus 3 is also 2x. So we kind of got a little bit of a problem there, which we'll address here in a moment. Let's do one more. What would the function big G of x have to be in order to get a derivative that is 3x squared? Well, it would have to be x cubed. Because if I take the derivative using the power rule, I'm going to multiply by that exponent. So I'm going to get my 3x. I'm going to subtract 1 to get my 2. But again, we have the same problem. I could add or subtract any number to this, and I'm still going to get that same derivative. So if you look at all these functions, f of x, g of x, and h of x, notice they're the same mother function, just with vertical translations, up or down, but they're all going to have the same derivative. So if we were to work backwards and take the antiderivative to get back up to f of x, well, in each case, the antiderivative of 15x squared, I hope we can see how that's going to get us to 5x cubed, but we're not going to get that plus 7, and we're not going to get that minus 2, and that's a problem. If you think about it in terms of the actual graphs, let's say we have some function that looks like this purple graph right there, and we have some other function that has the same shape but is shifted up compared to some other function with the same shape but shifted down. Remember that the derivative of a function is representing the slope of the function. So the derivative of all three of these is going to be exactly the same, even though the functions themselves are different. And for that reason, anytime we take an antiderivative, we always need to add this c right there, the constant of integration. If we integrate the function 3x squared, we will get x cubed plus that c, that constant of integration. And that c is accounting for the fact that we have infinitely many graphs that we could end up with, either shifted up or down. We don't know which, so we say plus c to represent all of them. So briefly, notice the integral notation here. When you hear me say antiderivative or integral, I'll be typically talking about the same thing. They're more or less synonymous, but I have the integral of 3x squared dx equals x cubed plus c. So that goofy symbol right there, that is your integral symbol. That is telling me to integrate this function, which means take the antiderivative of the function and add that constant of integration, c. That dx right there should be familiar to you. You should remember from our derivative unit that dy over dx is the same as saying y prime, the derivative of y with respect to x. All it's saying is that x is the variable we are interested in. So if this function said the integral of 3t squared, it would say then dt, and it would tell you you're integrating with respect to the variable t. So let's do one more real quick. Let's say, what is the integral of 3x squared plus 2x plus 1? What is the indefinite integral here? Well, 3x squared is going to go to x cubed, plus 2x is going to go to x squared, plus 1 is going to go to x, and then we have our plus the constant of integration c right there. But let's put this a little more generally. Let's come up with a rule. Given the power rule, if we have some function x to the n, how do we get the derivative? Well, we subtract 1 from the exponent, n becomes n minus 1, and we multiply by that original exponent. The n goes down, giving us that n right there. Well, let's work backwards. If I have the derivative and I want the antiderivative, think about from that n minus 1, how did I get to n? Well, I had to add 1 to the exponent. And then what did I do once I added that 1 to the exponent? Well, then I divided by the new exponent. So add 1 to the exponent, and then divide by the new exponent. If you think about it in terms of order of operations backwards, by taking an antiderivative, we are undoing whatever process we did to get the derivative. So since when we took the derivative, we multiplied and then subtracted 1, now we have to add 1 and then divide by that new number, working backwards, undoing it. So if we have some function like this, x to the n, we know we're going to take that n, we're going to add 1 to it, and then we're going to divide by that new value to get our integral is x to the n plus 1 over n plus 1 plus c, that constant of integration. Add 1 to the exponent, and then divide by whatever you get. So let's do a couple practice problems real quick. We want to know what is the integral of x cubed minus x dx. Well, integrate each piece. X cubed, we need to add 1 to the exponent, so it becomes x to the 4th, and we need to divide by that new exponent. Then subtracting x is going to become x squared, adding 1, and then dividing by that exponent over 2, and then plus our constant of integration, and that is our indefinite integral right there. Do one more quick one like this. What is the integral of the function 4x squared minus 3 dx? Well, that's going to be x squared is going to go to x cubed, and then we're going to divide by that new coefficient, which is 3, minus, same thing, 3 there is going to go to 3x, and then we have our plus c, constant of integration. So a few more indefinite integrals that we want to do here. I'm going to have to remember a few things from our derivative unit. Sometimes before we can take the derivative or antiderivative, we need to rewrite our equation so that we can use the power rule. So anytime we have an x term in the denominator, we can always rewrite it in the numerator with a negative exponent instead of a positive one. So 1 over x cubed is going to become x to the negative third. Remember that negative exponent just means move it down to the bottom. So I can rewrite that in that form, and now I can use the power rule. So I'm going to add 1 to my power. So negative 3 plus 1 gives me negative 2, and then I need to divide by that new power, so divided by negative 2, and then I have my plus c. Let's write this in a little cleaner fashion. Let's say negative 1 over 2x squared plus c. That'll be our final answer right there. Similarly, when we have a square root, or any root for that matter, we need to rewrite that first as a fractional exponent. So if we're taking the integral of the square root of x, it's the same as the integral of x to the power of 1/2. Remember, when you have a fractional exponent, the numerator of the fraction represents the power, and the denominator represents the root. And so now we can integrate that with respect to x, and we will add 1 to the power, so x to the 1/2 plus 1 will get us to 3/2, and now we need to divide by that 3/2, add our constant of integration c. Now remember, dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So I'm going to rewrite this as 2/3 x to the 3/2 plus c, and that will be my final form right there. Almost done, but a couple more things to point out. When you're dealing with a fraction like this, we don't know how to take the derivative or the indefinite integral of a quotient, a fraction like that, nor a product for that matter. And so before we can integrate, we need to rewrite this function. So split that fraction up into two different pieces, x to the 5th over x plus the square root of x over x. And now we want to go a little bit further. X to the 5th over x becomes x to the 4th. And square root of x, remember, square root of x is the same as x to the 1/2. So we have x to the 1/2 over x. We'll think about how those powers are working together. You subtract the power of the numerator by the power of the denominator. So we're going to get 1/2 minus 1 gives me an x to the negative 1/2. And now this is something I can integrate. X to the 4th becomes x to the 5th over 5, plus x to the negative 1/2 becomes x to the positive 1/2, divided by that 1/2, which we will now simplify. X to the 5th over 5, plus dividing by 1/2 is the same as multiplying by 2, so I have 2 root x, and then don't forget that constant of integration. That right there is our indefinite integral. If I were to give you a problem like the integral of x plus 3 quantity times quantity x minus 2, it's going to be the same idea. We don't know how to integrate a product like that, and so we're going to need to FOIL that out and then integrate the result. So we could say that's the same as x squared, let's see, plus x minus 6, and then you could integrate each piece from there. So we get x cubed over 3 plus x squared over 2 minus 6x plus c. So anytime you have a product or a quotient, before you can use your power rule for integration, you need to rewrite it and simplify it into just the sum or difference of a few different terms. So to summarize real quick, derivatives represent the slope of a function. They take us down a degree. Integration goes the opposite direction. Integration, antiderivatives, going the other way. So if you think of the power rules, power rule for derivatives is subtract 1, multiply by the original number. Power rule for integration is add 1 and then divide by that new exponent.